Welcome to week 7 of Big Data Analytics. Over the past weeks, we have built a strong foundation in distributed data processing. We started with HDFS, which gave us reliable storage across clusters. Then we explored MapReduce, which introduced us to parallel computation through the map and reduce paradigm. After that, we studied Hive, which brought SQL-like querying to our big data ecosystem. However, all these tools share a common limitation. They rely heavily on disk I/O. Every intermediate result gets written to HDFS, serialized, compressed, and replicated. This works well for simple batch jobs, but what happens when we need to run iterative algorithms like machine learning models that require multiple passes over the same data? This is where Apache Spark comes in. Today we will explore how Spark keeps data in memory, introduces the concept of resilient distributed data sets, and fundamentally changes how we think about big data processing. Now let us look at what we will cover today. We will begin with a brief recap of MapReduce limitations and understand why Spark was developed as a solution. Then we will examine the Spark cluster architecture to see how the driver, executors, and cluster manager work together. After that, we will introduce the core abstraction in Spark, resilient distributed data sets, or RDDs. We will learn how RDDs enable in-memory computation and fault tolerance. Next, we will distinguish between two fundamental types of operations: transformations, which are lazy and define a computation pipeline, and actions, which trigger actual execution. We will then explore key value RDDs, which are essential for aggregation operations at scale. Finally, we will look at the Spark Web UI, a powerful tool for monitoring and debugging your applications. Let us begin with the motivation behind Spark. Let me give you the roadmap for today's lecture. We will start with a recap and motivation, revisiting what we learned about MapReduce and understanding why we need Spark. Then we will explore the Spark cluster architecture to see how Spark distributes computation across multiple machines. Next comes the core abstraction, RDDs, or resilient distributed data sets, which are the fundamental data structure in Spark. We will then distinguish between transformations and actions, two types of operations that behave very differently. After that, we will dive into key value RDDs, which are particularly important for aggregation operations at scale. We will also examine the Spark Web UI, a practical tool for monitoring and debugging your applications. Finally, we will summarize the key takeaways. Let us begin by understanding why Spark was created in the first place. Before we dive into the technical details, let us clarify what you should be able to do by the end of today's session. First, you will understand why Spark outperforms MapReduce, especially for iterative workloads like machine learning algorithms. Second, you will describe the Spark cluster architecture, including the roles of the driver, master, workers, and executors. Third, you will distinguish between transformations, which are lazy operations, and actions, which trigger actual computation. Fourth, you will create and manipulate RDDs using PySpark, the Python API for Spark. Finally, you will learn to read the Spark Web UI to monitor job execution and debug performance issues. Throughout this lecture, we will use the Chicago Crimes dataset stored on HDFS, the same dataset we queried using Hive in previous weeks. This continuity will help you compare how Spark and Hive handle the same data differently. Before we dive into Spark, let us revisit what we learned about MapReduce and understand why we need something better. MapReduce gave us three fundamental capabilities: horizontal scalability, meaning we can add more machines to process larger data sets; fault tolerance, so the system recovers automatically from failures; and data locality, which means computation moves to where the data resides. However, MapReduce comes with a significant cost. After every map and reduce stage, all intermediate data must be written back to HDFS. This means serializing the data, compressing it, and replicating it 3 times across the cluster. As a consequence, iterative algorithms suffer tremendously. Imagine a machine learning algorithm that runs 10 iterations. With MapReduce, this translates to 20 complete HDFS read and write cycles. This is precisely the problem Spark was designed to solve. Let us be more specific about where MapReduce excels and where it fails. On the one hand, MapReduce is excellent for one-pass jobs, ETL pipelines, batch aggregations, and log processing. These workloads read data once, transform it, and write the result. On the other hand, MapReduce becomes painfully slow for iterative algorithms. Machine learning models that require dozens of passes over the same data set, graph algorithms like PageRank that iterate until convergence, and interactive queries where analysts explore data repeatedly, all of these suffer from the disk I/O bottleneck we just discussed. As Zaharia and his colleagues observed in their seminal 2010 paper, many algorithms require passing over the same data dozens of times, and MapReduce makes this prohibitively slow. This observation led directly to the creation of Apache Spark. So how do we solve this problem? The core idea behind Spark is elegantly simple. Instead of writing intermediate results to disk after every operation, keep them in memory. This is where the concept of the resilient distributed data set, or RDD, comes in. An RDD is a read-only partitioned collection of data that lives in RAM across the cluster. Now you might ask, what happens if a node fails and we lose part of the data? Spark achieves fault tolerance through lineage. It remembers how each partition was computed. So if a partition is lost, Spark can simply recompute it from the original source. As a consequence, there is no need to replicate data across nodes like Hadoop does. This in-memory approach makes Spark 10 to 100 times faster than MapReduce on iterative workloads. We will see how RDDs work in detail shortly. Now let us understand what an RDD actually is through a simple analogy. Think of an RDD as a recipe, not the cooked meal itself. When you write code to transform data, you are simply writing down instructions. Spark does not execute them immediately. This brings us to three key properties. First, distributed. Your data is split into partitions across workers. If your file is 400 megabytes and you have 4 workers, each gets 100 megabytes. Second, resilient. If a worker crashes, Spark remembers the recipe and recomputes the lost partition from scratch. Third, lazy. Nothing happens when you write transformations like map or filter. Spark only executes when you call an action, such as count or collect. As such, transformations are lazy recipes, while actions cook the meal. An RDD is essentially a snapshot of your data, plus the instructions to rebuild it if needed. Now let us compare MapReduce and Spark side by side to see why Spark is faster. Imagine you have 3 jobs to run sequentially. In MapReduce, each job reads from disk, processes the data, then writes the result back to disk. The next job must wait, read from disk again, process, and write again. This means every intermediate result hits the disk, which is extremely slow. On the other hand, Spark keeps intermediate results in memory. The first job loads data into memory, processes it, and passes the result directly to the next job without touching the disk. Only the final output is written to disk. As a consequence, Spark eliminates the repeated disk input-output overhead, making it up to 100 times faster than MapReduce for iterative workloads. This is why Spark is the preferred framework for machine learning and iterative analytics. Let us look at a concrete performance comparison between MapReduce and Spark. The figure shows execution time for an iterative machine learning algorithm called logistic regression. Notice how MapReduce execution time remains constant across iterations because it reads from disk every single time. However, Spark shows a dramatic difference. The first iteration takes time to load data into memory, but subsequent iterations are significantly faster because the data is already cached. This performance gap becomes more pronounced as the number of iterations increases. For example, after 10 iterations, Spark completes the task in a fraction of the time MapReduce requires. This demonstrates why Spark is particularly well suited for iterative algorithms such as machine learning models and graph processing algorithms like PageRank, where the same data set must be processed repeatedly. Now that we have seen why Spark outperforms MapReduce for iterative workloads, let us dive deeper into how Spark actually achieves this performance. To understand Spark's capabilities, we need to answer several fundamental questions. First, how is Spark organized as a distributed system? What are the key components that make up a Spark cluster? Second, what is the core abstraction that enables Spark to process data in memory? Third, how does Spark distinguish between operations that transform data and operations that trigger computation? And finally, how can we monitor and debug our Spark applications? In this lecture, we will address each of these questions systematically. We will begin by examining Spark's cluster architecture and understanding the roles of the driver, executors, and cluster manager. Then we will explore RDDs, the fundamental data structure in Spark. We will also learn about transformations, actions, and key value operations that enable large-scale aggregations. Let us now examine the architecture of a Spark cluster. Imagine that you have a large data set distributed across multiple machines, and you want to process it in parallel. To achieve this, Spark uses a master worker architecture with three main components. First, we have the driver program, which runs on the master node and contains your application code. The driver is responsible for coordinating the entire computation. Second, we have the cluster manager, which allocates resources across the cluster. This could be Yarn, Mesos, or Spark's standalone manager. Third, we have the worker nodes, each running one or more executors. These executors are the processes that actually perform the computations and store data. As a consequence, when you submit a Spark application, the driver communicates with the cluster manager to obtain executors, then distributes tasks to these executors for parallel execution. We will now examine each component in detail. Let us now understand the specific role of each component in the Spark architecture. First, the driver hosts the Spark context, builds the directed acyclic graph of operations, and schedules stages for execution. The Spark context itself serves as the entry point to Spark and connects to the cluster manager. The cluster manager, which in our case is Yarn, allocates resources across the cluster. Executors are JVM processes running on each worker node that execute tasks and hold cached data. Tasks represent the smallest unit of work and operate on a single partition. Finally, the cache provides in-memory storage for persisted RDDs. It is important to note that in MapReduce, each task runs in its own JVM, which incurs slow startup overhead. However, in Spark, an executor JVM stays alive for the entire application and runs many tasks, resulting in much lower overhead and faster execution. Now let us understand how a Spark job runs step by step through a concrete example. Imagine that you submit a Spark application that performs a word count on a large text file. The driver program first creates a logical execution plan by analyzing all the transformations in your code. However, Spark does not execute transformations immediately. Instead, it waits until an action is called, such as count or collect. At that moment, the driver divides the job into stages. A stage boundary occurs whenever data must be shuffled across partitions, for example, during operations like reduce by key, group by key, or join. Within a single stage, tasks pipeline transformations without writing intermediate results to disk, which is why Spark is so fast. Each stage is then broken into tasks, one task per partition, and these tasks are scheduled on executors across the cluster. We will walk through this process in detail next. Now that we understand how the driver schedules tasks, let us see how Spark actually loads data into memory. Imagine that your data set is stored in HDFS split into 4 blocks, A, B, C, and D. Worker 1 holds blocks A and B, while worker 2 holds blocks C and D. When an action is triggered, Spark follows 2 important principles. First, data locality. Each task runs on the machine that already holds its block, avoiding network transfer. Second, partitioning. Each HDFS block becomes one RDD partition loaded into the executor's RAM on that worker. It is important to note that Spark uses lazy loading. Data enters memory only when an action is called, not during transformations. Furthermore, caching is selective. You must explicitly call .cache if you want an RDD to remain in memory, nothing is cached by default. As a consequence, processing is both parallel and local, minimizing data movement across the network. Now, what happens if the worker runs out of memory? Spark's answer is simple: spill to disk. However, you can control this behavior by choosing a storage level when caching your RDD. And let us examine the available options. First, memory only, which is the default. It stores data in RAM and recomputes lost partitions if memory is insufficient. This is fast if your data fits in memory. Second, memory and disk, which stores data in RAM first, then spills overflow partitions to disk. This is slower for reads but avoids recomputation. Third, disk only, which always stores on disk. Use this only as a last resort. Fourth, memory only SER, which serializes data in RAM, saving space at the cost of CPU overhead. In practice, use memory only by default. If you see spill metrics in the Spark UI or encounter out-of-memory errors, switch to memory and disk, or allocate more executor memory using the executor memory flag. Now that we understand persistence strategies, let us see how to actually run Spark on our cluster. Our environment consists of Hadoop 3.4.1 with Yarn, one master node, and 2 worker nodes. To start an interactive PySpark shell, you use the PySpark command with the master flag set to Yarn. For submitting a standalone script, use Spark submit with the same master configuration. Notice the deploy mode flag. Client mode runs the driver on your local machine, which is useful during development, while cluster mode runs the driver on a worker node, which is recommended for production. While a job is running, you can monitor it through the Yarn Resource Manager at port 8088 and the Spark UI at port 4040. Remember, the Spark UI is only active during job execution. Now that we understand how to deploy Spark on a cluster, let us move to the heart of Spark programming, the RDD, or Resilient Distributed Dataset. To master Spark, we need to answer several fundamental questions. First, what exactly is an RDD, and why is it the core abstraction in Spark? Second, how do we create RDDs from our data sources? Third, how does Spark partition our data across the cluster, and why does partitioning matter for performance? In this section, we will address each of these questions systematically. We will explore the 3 key properties that make RDDs powerful: immutability, lazy evaluation, and partitioning. We will examine the 3 main ways to create RDDs in practice. Finally, we will understand how partition count affects parallelism and performance. Let us begin by understanding what an RDD actually is. Let us start by understanding what an RDD actually is. Imagine that you have a large data set distributed across multiple machines in a cluster. An RDD, or Resilient Distributed Dataset, is Spark's way of representing this distributed collection of data. Think of it as a logical abstraction that allows you to work with data spread across many nodes as if it were a single collection. Now, RDDs have 3 fundamental properties that make them powerful. First, they are immutable, which means that each transformation you apply creates a new RDD rather than modifying the existing one. Second, they are lazily evaluated, meaning that Spark does not execute any computation until you call an action. Third, they are partitioned, where each partition represents a chunk of data that will be processed by a single task in parallel. These 3 properties work together to enable Spark's efficiency and fault tolerance. Now that we understand what RDDs are, let us see how to create them in practice. There are 3 main ways to create an RDD in Spark. The first method is to parallelize an existing collection in your driver program. For example, if you have a Python list containing the numbers 1 through 5, you can call Spark context, parallelize on that list to create an RDD. The second method is to load data from an external storage system, such as HDFS. Here we use Spark context.txt file to read the file, where each line in the file becomes one string element in the RDD. The third method is to transform an existing RDD using operations like map or filter. Notice the parameter num partitions, which controls the degree of parallelism. By default, when reading from HDFS, Spark creates one partition per HDFS block. Let us now visualize how RDD partitions are distributed across the cluster. Imagine we have an RDD containing the numbers 1 through 9. This RDD is divided into 3 partitions. The first partition contains elements 1, 2, and 3. The second partition holds 4, 5, and 6. And the third partition contains 7, 8, and 9. Each partition is processed independently on a different worker node in the cluster. This is the essence of parallel processing in Spark. However, it is important to note that more partitions lead to more parallelism, but also introduce more scheduling overhead. As a general rule, aim for 2 to 4 partitions per CPU core in your cluster. This balance ensures efficient parallelism without overwhelming the scheduler with too many small tasks. Now that we understand how Spark partitions data for parallel processing, let us move to the heart of Spark programming: transformations and actions. In this section, we will answer 3 fundamental questions. First, what are transformations and how do they build the execution plan? Second, what special transformations exist for key-value pairs? And third, what are actions and how do they trigger the actual computation? It is important to note that Spark follows a lazy evaluation model. This means transformations do not execute immediately. Instead, they build a directed acyclic graph or DAG of operations. Only when an action is called does Spark execute the entire plan. This lazy approach allows Spark to optimize the execution pipeline before running any computation. Let us examine each concept in detail. Let us begin with transformations. A transformation takes an RDD and returns a new RDD. However, no computation happens yet. This is the essence of lazy evaluation. For example, the map transformation applies a function to every element, such as parsing a CSV row into a tuple. The filter transformation keeps only elements where a condition is true, like removing a header row. The flat map transformation performs a one-to-many mapping. For instance, converting sentences into individual words. The distinct transformation deduplicates elements, such as finding unique crime types. Finally, the union transformation merges 2 RDDs, like combining data from 2 files. As a consequence of this lazy approach, Spark optimizes the full pipeline before executing. Unnecessary computations are skipped entirely. This is why transformations are efficient and form the backbone of Spark's computational model. Now, when your RDD contains key-value pairs, a new set of powerful transformations becomes available. Let us examine the most important ones. First, reduce by key applies a function to combine all values sharing the same key. For example, summing crime counts per district. Second, group by key collects all values for each key into a list, such as grouping all crimes by district. Third, sort by key orders the RDD by its keys, like alphabetically sorting crime types. Fourth, join performs an inner join between 2 RDDs on their keys, for instance, matching crimes with district information. Finally, map values applies a transformation only to the values while keeping the keys unchanged. However, it is important to note that reduce by key, group by key, join, and sort by key all trigger a shuffle operation, meaning data is exchanged across the network. This is the most expensive operation in Spark. Now we move from transformations to actions. Remember that transformations are lazy, meaning they do not execute immediately. Actions, on the other hand, are eager. When you call an action, Spark triggers the computation of the entire DAG and returns a result to the driver program. Let us look at the most common actions. First, count returns the number of records in the RDD. Second, first retrieves the first element, useful for quick inspection. Third, take of n returns a list of the first n records for previewing data. Fourth, collect brings all data to the driver as a list. However, be very careful with collect. On a 50 gigabyte data set, this will crash your driver with an out-of-memory error. Always use take for previews instead. Fifth, a reduce applies a function to aggregate all elements into a single value, like computing a sum. Sixth, save as text file writes the RDD to HDFS or local storage. Finally, count by key returns a dictionary, counting occurrences per key. Now that we understand what actions do, let us address a critical question. Why does Spark use lazy evaluation in the first place? Imagine you build a pipeline with 10 transformations followed by a single action. Without lazy evaluation, Spark would execute each transformation immediately, writing intermediate results to disk at every step. However, with lazy evaluation, Spark waits until the action is called, then analyzes the entire pipeline as a whole. As a consequence, Spark can optimize the execution plan before running anything. And for example, if a filter operation eliminates 95% of your data early in the pipeline, Spark will push that filter as close to the source as possible, avoiding unnecessary computation on data that will be discarded anyway. Furthermore, transformations are pipelined within tasks, meaning no intermediate materialization occurs between stages. This dramatically reduces disk I/O and speeds up execution. Now, an important question arises. What happens if a partition of an RDD is lost due to a node failure? This is where RDD lineage becomes critical. Every RDD maintains a record of the transformations that created it, forming what we call a lineage graph. Let us understand this through an example. Suppose we have a text file in HDFS and we apply a filter transformation followed by a map transformation. If partition 0 of the map RDD is lost, Spark does not need to recompute everything from scratch. Instead, it replays only the necessary lineage. It rereads that specific partition from HDFS, applies the filter, then applies the map. As a consequence, no data replication is needed. This lineage-based fault tolerance is one of Spark's most elegant features, making it both efficient and resilient. Now that we understand how RDDs work and how Spark handles fault tolerance through lineage, let us move to a critical topic for big data analytics: aggregation at scale. In this section, we will focus on key value RDDs, which are the foundation for all group by operations in Spark. Imagine you have millions of records and you need to aggregate them by category. For example, counting crimes by type or summing sales by region. This is where pair RDDs come into play. We will explore how to create key value pairs, how to aggregate them efficiently using operations like reduce by key, and why choosing the right aggregation method matters for performance. We will also walk through a complete example using the Chicago crimes dataset to see how Spark orchestrates these operations across a cluster. Let us now understand the foundation of all aggregation operations in Spark, the pair RDD. A pair RDD is simply an RDD where each element is a tuple consisting of a key and a value. This structure is essential because it enables group by analytics at scale. Look at the code example on the slide. We start with a simple RDD containing strings. By applying the map transformation, we convert each string into a key value pair, where the first character becomes the key and the entire string becomes the value. This creates our pair RDD. Most analytics in Spark follow a three-step pattern. First, we create pairs from our raw data. Second, we aggregate these pairs by their keys using operations like reduce by key. Third, we sort the results to extract insights. This pattern is fundamental to distributed data processing. Now let us understand why reduce by key is superior to group by key through a concrete scenario. Imagine that we have millions of records distributed across multiple worker nodes, and we want to count occurrences by key. If we use group by key, it shuffles all values across the network to group them together. As a consequence, this materializes all values in memory on a single node, which creates a serious risk of out-of-memory error when dealing with large data sets. However, reduce by key applies a combiner function locally, first on each partition, performing partial aggregation before shuffling. As such, it shuffles only the partial aggregates across the network, not the raw values. This is much more memory efficient and network efficient. It is important to note that reduce by key works only for associative and commutative operations like sum, count, or max. Always prefer reduce by key over group by key whenever your operation satisfies these properties. Now let us put everything together with a complete example. Imagine we have the Chicago crimes dataset and we want to find the top 5 most frequent crime types. The full RDD pipeline works as follows. In stage 0, we start by loading the text file, then filter out the header row. Next, we map each line to extract the crime type, filter out any null values, and map each crime type to a key value pair with count 1. At this point, reduce by key performs local combining within each partition, summing up the counts. Then comes the shuffle phase, where partial counts are exchanged by key across all workers. In stage 1, the partial counts are merged together, sorted in descending order. And finally, we take the top 5 results, which are returned to the driver. This demonstrates the full power of RDD transformations and actions working together efficiently. Now let us look at another practical example, counting arrests per police district. And we start by loading the crimes dataset and filtering only those records where an arrest was made. Next, we extract the district field from each record and map it to a key value pair, where the key is the district and the value is 1. Then we apply reduce by key to aggregate these counts, summing up all arrests per district. Finally, we sort the results in descending order using sort by with the second element of each tuple, which is the count, and we set ascending to false. The collect action brings all results back to the driver. This pattern of filter, map, reduce, and sort is extremely common in big data analytics, and you will use it frequently when analyzing large data sets. Now that we have seen how to write Spark transformations and actions, let us turn our attention to a critical tool for understanding what happens when your Spark job runs, the Spark Web UI. When you submit a Spark application, Spark automatically launches a web interface that provides detailed insights into your job's execution. This interface answers several important questions. How many stages did my job create? Remember, the number of stages equals the number of shuffles plus 1. How many tasks ran in each stage? This corresponds to the number of partitions at that point in the computation, how much data was shuffled across the network, and where did the bottlenecks occur. Understanding the web UI is essential for debugging performance issues and optimizing your Spark applications. Let us explore how to read and interpret this interface. When you open the Spark Web UI, you will see several key metrics that help you diagnose your application's performance. First, look at the stages section. The number of stages tells you how many shuffles occurred in your job using the formula number of stages equals number of shuffles plus 1. Next, examine the tasks per stage. This number directly corresponds to the number of partitions at that point in the computation. The shuffle write and read metrics show you how much data was transferred across the network during shuffle operations. Finally, pay attention to the duration column. This helps you identify slow tasks, also called stragglers, which can significantly impact your job's overall performance. By monitoring these 4 metrics together, you can pinpoint exactly where your Spark application is spending its time and where optimization is needed. Now, let us understand a critical concept called data locality, which directly impacts task performance. Imagine that Spark schedules a task to process a partition of data. The question is, where is that data physically located? Is it in the same executor's memory, on the same node, or somewhere far away on a different rack? Spark classifies this into 4 locality levels. The best case is process local, meaning the data is already cached in the same executor's JVM. This is the fastest. Next is node local, where the data is on the same physical machine. Then comes rack local, where data is on the same rack but a different node. The worst case is any, meaning the data is on a completely different rack, requiring expensive network transfers. As a consequence, tasks marked as any are slow because data must move across the network. Spark actually waits briefly for a better locality slot before downgrading to a worse level. You can control this waiting time using the spark.locality.wait configuration parameter. To check locality levels in practice, go to the Stages tab and examine the task details. We have now reached the end of this lecture on Apache Spark. Let us take a moment to review what we have covered today. We began with a recap and motivation. understanding why Spark was developed to overcome the limitations of MapReduce. We then explored the Spark cluster architecture, including the driver, cluster manager, and executors. We introduced RDDs as the core abstraction in Spark, explaining their immutable and distributed nature. We examined transformations and actions, understanding the lazy evaluation model. We also covered key value RDDs and how they enable powerful aggregation operations at scale. Finally, we walked through the Spark Web UI to monitor and debug our applications. In the next session, we will move beyond RDDs and explore Spark data frames and Spark SQL, which provide higher-level APIs for structured data processing. Let us now consolidate what we have learned about Spark in this lecture. First, Spark fundamentally replaces MapReduce's disk-based model with in-memory processing. As you can see in the table, MapReduce follows a cycle of read, process, write to disk, and repeat, which creates significant I/O overhead. Yet in contrast, Spark reads data once, then performs multiple transformations in RAM before executing an action. Second, recall the architecture. The driver coordinates work through a cluster manager, which distributes tasks to workers running executors. Third, RDDs are immutable, lazily evaluated, distributed, and fault-tolerant through lineage tracking. Fourth, transformations like map and filter build a DAG without executing, while actions like collect trigger computation. Fifth, for aggregations, prefer reduce by key over group by key for efficiency. Finally, always use the web UI at port 4040 to monitor jobs, stages, tasks, and shuffle metrics during development and debugging. Looking ahead to our next session, we will move from low-level RDDs to higher-level APIs that make big data processing simpler and faster. We will introduce data frames, which are distributed tables with named typed columns similar to tables in a relational database. You will learn how to load data from CSV, JSON, and Parquet files using spark.read, and how to apply transformations like select, filter, group by, and join. We will also explore Spark SQL, which allows you to register data frames as views and query them using standard SQL syntax. Importantly, we will explain the Catalyst optimizer and why data frames often outperform RDDs. Before the next lecture, please SSH to the cluster, launch PySpark in yarn mode, load the Chicago Crimes dataset from HDFS, and verify that you get 10,001 rows. This hands-on preparation will ensure you are ready for the data frame exercises.